Math and Beats. In this video, what we're going to do is look at some properties of indefinite integrals and also some of the initial rules that are needed to move further in the topic of antiderivatives. Let's go. All right, now just to refresh, when we have this symbol right there, that is our indefinite integral of the function f of x with respect to x, and that gives us the general family of antiderivatives of the function f of x. Thus, when we find what this is, we will result in some, say, big f of x plus some constant, where big f of x is some antiderivative of the function little f of x. So that's just to refresh our memory, and the focus here is to explore some more types of things that go along with this indefinite integral. So, a couple of rules or properties, if you will, to get us going. The first one, constant multiple rule for indefinite integrals. Assuming you have a real constant c, then if I want to integrate a constant times the function f of x with respect to x, that is the same as the constant c times the indefinite integral f of x dx. This should seem reasonable because we have already established the rule that if I differentiate a function with respect to x, say c times f of x, then we know this is the same as c times the derivative with respect to x of f of x. And so we're just going the backwards direction. That constant should just stick around for the ride. So, same goes for indefinite integrals. A couple other initial rules or properties, if you will, of indefinite integrals, the sum and difference rules for indefinite integrals. If I want to find the integral of f of x plus g of x with respect to x, then that is the same as the integral of f of x with respect to x plus the integral of g of x with respect to x. And correspondingly, down here, very similar, if I want to integrate f of x minus g of x with respect to x, that's going to be the same thing as the integral of f of x with respect to x minus the integral of g of x with respect to x. Again, we have already established the rule that if I take the derivative of two functions that are being added or subtracted with one another, say f of x plus or minus g of x, then we know that we can split those up and write this as the derivative of the function f of x with respect to x plus or minus the derivative with respect to x of g of x. So again, we're just going the backwards direction with our indefinite integrals, so this should seem like a reasonable thing to do. So we'll see some examples of this in this video when we look at more indefinite integrals. But first, to get us going, because this video is intended to just get us going with antiderivatives, no advanced techniques or rules yet, let's just kind of look at a few initial antiderivatives of some of the functions which don't involve more advanced techniques of finding. And so I got this table here, and on the left column we have a column with a variety of functions. In the right column we want to write the general antiderivative of the function that we have in the left column. So you start with the cosine of x. Which function has a derivative that is a cosine of x? That would be the sine x function, but don't forget that plus c, that constant there, right? So that one, fairly straightforward, but how about if we were given sine of x? What would its general antiderivative be? Well, in this case, it would actually be a negative cosine of x plus a constant. And that is because the derivative with respect to x, let's say, of negative cosine of x plus a constant is going to give us a negative sign, so that be giving us a positive sine of x. So, got to remember that the general antiderivative of the sine function is the negative cosine of x function plus a constant. Secant squared x, what is its general antiderivative? Well, that would be the tangent function. Tangent of x plus c, the derivative of the tangent function, is the secant squared function. How about e to the x? That might be the best of them all, huh? That would just be e to the x plus a constant, since the derivative of e to the x is e to the x, like so. We're also given 1 divided by 1 plus x squared. What is the general antiderivative of that? Well, which function has a derivative that is 1 divided by 1 plus x squared? That would be our arctangent or inverse tangent function plus a constant. Last two in this table. What is the general antiderivative of 1 divided by the square root of 1 minus x squared? Well, in this case, you could say it's the arcsine function of x, or the sine inverse function of x, plus a constant. Notice that you could also write here the negative arc cosine function of x plus a constant, since the derivative of the arc cosine function is the negative of 1 divided by square root of 1 minus x squared. So there's multiple options actually in that particular situation. And finally, in this table, the antiderivative, should I say the general antiderivative of negative cosecant squared of x, well, if you recall, that is the same as the cotangent of x function and plus that constant c. So this table is just supposed to get us going in the sense that, all right, we know a bunch of derivatives at this point of a bunch of functions. So if we're given a derivative of one of these functions, or even a constant multiple of one of these, can we say for which function that came from? Which function did we have to differentiate to get to its derivative? So there's more that is not written in this table. Think of all the other trigonometric functions and the other inverse trigonometric functions derivatives. But this is supposed to just kind of get an idea like, okay, there's a bunch that we can find without having to say do a backwards chain rule or a backwards product rule or things like that. We have some other rules that we're going to look at in this video. One of them is the general power rule for indefinite integrals, right? So if I give you a power function and say, what's the indefinite integral of this power function? Where did it come from? Well, then this is the rule that allows us to do that. Assuming that we have a number here, n, that is a real number, with n not equal to -1, we'll look at that -1 case later in this video, then the general power rule is for indefinite integrals that if I integrate a power function of the form x to the n with respect to x, we're going to get x to the n plus 1 divided by n plus 1 plus a constant. So I think like backwards process of differentiating a power function. And to verify this, we could simply differentiate with respect to x to the n plus 1 over n plus 1 plus that constant, and apply our power rule. That would give, well, that constant in front, 1 over n plus 1, the n plus 1 comes down from the power, and then lower that power by 1, giving us an x to the n, and of course the derivative of the constant is 0, n plus 1's cancel out, and we get just x to the n. So you can see it works out, and so if we are given any power function in an integral, and we want to go backwards to talk about its general antiderivative family, this is our general power rule. Of course, this does not work for n is equal to -1. We can see that because we'd be dividing by 0. And plus, that applies to some other specific rule, as we'll see at the end of this video. So now that we've said a few of these rules and talked about a few of the basic formulas for some of these antiderivatives, let's go and find a few indefinite integrals here. All right, so let's find a couple of them. In this first example, part A, we are asked to find the indefinite integral of the function 5x cubed minus 6x to the -4th. Now note, just to see the constant multiple rule and the difference rule at stake here, this is the same as writing 5 times the integral of x cubed with respect to x minus 6 times the integral of x to the negative fourth with respect to x. Right? So I can split up each of the functions into their own individual integrals and then combine them here, in this case through subtraction. And then each of those constant multiples I can pull out in front of the integral itself using the constant multiple rule. Now, once you do this enough times, you're not necessarily going to write it like that every time. However, it's nice to see it applying the rules that we previously talked about earlier in this video. Now it comes time for the integration process. Now remember, right above, what did we have? The general power rule that we had just written down, which was the integral of x to the n with respect to x is x to the n plus 1 over n plus 1 plus that constant, assuming that n is not equal to negative 1. And so we're going to apply to both of these integrals that rule now. So in this first one, we're going to have a 5 times an x to the 3 plus 1 power divided by 3 plus 1 in the denominator, minus a 6 times x to the negative 4 plus 1, all divided by negative 4 plus 1. And all of this plus a constant. Now, sometimes people will ask, well, don't we have a constant for each of these indefinite integrals? And surely that can be said to be true. But say for this one, I had some plus constant 1, and this one plus some constant 2, then at the very end, these constants would just get added together to give us some other constant, say c. So when we have an integral with multiple functions in it, we still just have a single constant added to the result for that reason. So that's why I'll write it like so in this step that we've just written. Let's clean this up. What do we get? All right, moving on. Well, this is going to give us a 5 over 4, x to the 4th power. And then we have a minus 6 over a negative 3 here, x to the negative 3 power, plus that constant. And finally, we can write this as 5/4 x to the 4th, and then plus a 2, x to the negative 3rd power plus that constant. So this right here is the general antiderivative, or the general family of curves, for which, when I differentiate, I get the function that we have in our integrand right above. So there's one example. Let's look at one more involving the power rule. This one, we have some fractional powers, and we also have some radical involved. Again, I could split this up into two different integrals and write it as 4 times the integral of x to the 3/7 power with respect to x, and then minus 2 times the integral. And right now we have a 5th root of an x to the 4th. So it is going to be helpful here if we turn this radical form into an exponential form so that we can actually apply the power rule. So 5th root of x to the 4th is the same thing as x to the 4/5 power. So on that second integral, I get a minus 2 times the integral of x to the 4/5 with respect to x. So fractional powers, same thing. We apply the general power rule, and we'll write this as a 4 times an x to the 3/7 plus a 1, all divided by 3/7 plus a 1, minus a 2 times an x to the 4/5 plus a 1 power, all divided by 4/5 plus 1, and then plus my constant of integration. And let's clean this all up. This is the same thing as 4x to the 10/7 power, all divided by 10/7, and then minus a 2 times x to the 9/5 power divided by 9/5 plus that constant. Clean this up a little more just so we don't have all these fractions sitting around. This is the same thing as a 4 times a 7/10 x to the 10/7 power minus a 2 times the 5/9 x to the 9/5 power plus that constant. And finally, we can write this as, well, 28 over 10 is the same thing as 14 over 5. So 14/5 x to the 10/7 power, and then minus a 10/9 x to the 9/5 power plus that constant. And so, again, this is the general family of curves that gives us the situation for which when I differentiate that family of curves, I always get my integrand right here, right? And, we're not checking, but the way to check if it is indeed correct is go ahead and differentiate our result. We better get back that integrand. So a couple of examples there involving the general power rule for indefinite integrals, and also using the sum and difference formulas along with the constant multiple rule as well. Another family of functions that we can take on here is, how about exponential functions? The general exponential rule for indefinite integrals here. In this situation, let's let the number b be a real number that's positive and not equal to 1. Hence, we're defining an exponential function here, as we would like to state what is the indefinite integral of an exponential function b to the x with respect to x. And the result is these functions of the form b to the x divided by the natural log of b plus a constant. Again, we can easily verify this by differentiating the result. So if I differentiate b to the x over the natural log of b plus a constant here, then the derivative of an exponential function of the form b to the x is the natural log of that base b times that function b to the x, but now it's being divided by the natural log of b. Derivative of the constant is 0. Natural logs of b's go away, and indeed we're left with the exponential function b to the x. So add it to the list of things that we can initially find antiderivatives of. So we'll look at a couple of examples of that right now as well to get some practice in. Let's find some more indefinite integrals. How about this integral right here? The indefinite integral of the function 3 to the x minus 2 to the negative x plus secant of x tangent of x with respect to x. Now I went ahead and just threw in a trigonometric function in there just for fun to keep us on our game. We can go ahead and rewrite this as the integral of 3 to the x with respect to x. And then notice we actually have a 2 to the negative x here. The rule above that we had stated was the integral of b to the x with respect to x is b to the x over the natural log of b plus a constant, assuming b is positive and not equal to 1. It didn't say nothing about a b to the negative x. So we need to rewrite that so that it is in the form so that it's an exponential function b to the x. And the way we do that is just rewrite it so it has a positive x as the exponent. So we're going to write this as a minus the integral of really a 1/2 quantity to the x power with respect to x, right? That's the same thing as 2 to the negative x. And then finally plus the integral secant of x tangent of x with respect to x. Now we can apply that rule that we've just talked about. So the first integral of 3 to the x is going to be the function 3 to the x over the natural log of that base 3 minus that function 1/2 quantity to the x all over the natural log of 1/2. And then think, which function has a derivative that is secant of x times tangent of x? Well, that is the secant function, secant of x here, plus our constant c. And if we chose to, we could rewrite that term right there so that the base was 2, but no real reason to do that. And there's our result, the family of curves, so that when differentiating that, we get back our integrand within the integral. Let's do one more of these at least. All right, how about the integral of 6 to the x plus 9 to the negative x, but now plus cosecant of x times the cotangent of x? Again, I can write this as integral of 6 to the x with respect to x, and then plus here integral, again, we have that negative x, so we want to turn that to a positive x power, and thus I will write this as a 1/9 as a base to the positive x power with respect to x, and finally plus the indefinite integral of the cosecant of x times cotangent of x function with respect to x again. Applying our exponential rules, we get for the first integral 6 to the x divided by the natural log of 6, and then plus a 1/9 to the x over the natural log of 1/9, and then think, oh, which function has a derivative that's equal to the cosecant of x times the cotangent of x? And in fact, that would be the negative cosecant of x function plus that constant here. And so you think again, okay, well, we know the derivative with respect to x of the cosecant function is going to be equal to the negative of cosecant of x times the cotangent of x. So if I have the derivative with respect to x of a negative cosecant of x function, this would be negative negative of that result, giving us a positive cosecant of x times cotangent of x. And hence, we get our family of curves once again. Lots of good stuff so far. And we've talked about a lot of the functions we know we can find antiderivatives of so far in this video. However, there is this one situation that I want to finish the video off with, which has to do with this integral right here, the indefinite integral of 1 over x dx. We are asked to investigate this. We are detectives now. Let's figure this out. Okay, so we know something, right? From our derivatives knowledge, we know the derivative of the natural log of x function is equal to 1 over x. So one might think, is it true that this indefinite integral that we're looking for, the integral of 1 over x with respect to x, is that the natural log of x plus a constant? Sometimes that would seem intuitive to start with. However, as we're going to see, that is not true. And let's see why. The domain of the function ln of x, of course, is positive real numbers, 0 to infinity, not including the 0. And so when we differentiate the natural logarithmic function with respect to x, and we say, oh, its derivative is 1 divided by x, like we've established, what we're really saying is that is its derivative, but only on the interval for which the natural log of x is actually defined, right? And that is for positive real numbers. So it's not true otherwise. It's only true for those values of x. And here's a graph just to depict that idea, right? So the blue graph is my natural log of x function, and then the red graph is its derivative, 1 over x. But as we can see, this is only happening for values of x that are positive. Now, the natural log of x is, of course, defined for only positive real numbers. But the function 1 over x is actually defined for a lot more numbers other than this. And so that's what we're kind of getting at here. If we actually start now with the function, say, y is equal to 1 over x, well, that has a domain that is actually all real numbers excluding 0, and hence negative infinity to 0 union with 0 to infinity. And so when we're asked to find the family of curves that have derivatives equal to 1 over x, it cannot be the natural log of x plus c, because if we start with the natural log of x and we differentiate it, then its derivative will not have a domain that is at least all of these numbers, all real numbers excluding 0. So there's no way that that can happen. And so we have to think a little bit deeper here. Okay, if I'm now starting with this function 1 over x, there's got to be another function such that its derivative actually is 1 over x for all real numbers excluding 0. Now, before we investigate further, we can say that at least for positive values of x, this is true, that the antiderivative family of 1 over x dx is the natural log of x plus c. However, we need to figure out what's going on when x is negative, because that's not going to be true if x is negative. Clearly, natural log of x isn't even defined then. So how to do this? Well, take note of this result. If I differentiate the natural log of negative x with respect to x, simple chain rule, I'm going to get a negative 1 divided by negative x, which of course is the same as 1 divided by x. And note that the domain of the natural log of negative x is actually all negative numbers. So negative infinity to 0. Let's go ahead and just define the natural log of the absolute value of x. So this is a piecewise defined function that gives us, okay, it's going to be the natural log of x if x is positive, and it's going to be the natural log of negative x if x is negative. And so once we define that and combine that with the statement right above and the statements prior to that, then it follows that the derivative of the natural log of the absolute value of x is 1 over x for all real values of x that are non-zero. And so it shows what the result is that we're actually looking for, and that is the general family of curves that have a derivative of 1 over x is not natural log of x plus a constant, but the natural log of the absolute value of x plus a constant. And so that's really important to note, right? And you compare that with the derivative of the natural log of x, which is 1 over x. Again, this is only true if x is positive, right? But this right here is true if x is non-zero. So negative and positive values of x, which is exactly what we needed. And to wrap it up, show a graph of exactly this idea. So before, we just saw this picture, right? But now we see the entirety of the graph of 1 over x given to us, and also the graph of the natural log of the absolute value of x, the blue graph. If I start with the natural log of absolute value of x, and I think about its slope, well, for negative values of x over here, right, this function is decreasing, and its derivative should be negative, for which it certainly is. For positive values of x over here, it's the same situation as before, that we have the derivative of the natural log of x is 1 over x. And so now we can see is, okay, if I'm asked to find the indefinite integral of 1 over x dx, that's that red graph there, right? And that is the derivative of the natural log of the absolute value of x. So that's a big result, and take note of it, add it to the list. And that, my friends, is the end of this video. So a variety of things we talked about in this video, including constant multiple rules for indefinite integrals, sum and difference rules for indefinite integrals. We saw the general power rule for indefinite integrals. We saw the general exponential rule for indefinite integrals. And then we found some of these, right? And then we also investigated this special case of the indefinite integral of 1 over x with respect to x. So hopefully that gives a broader picture of some of our antiderivatives that we can tackle as of now. In the next video, we're going to look at a few more examples before we wrap this discussion up. So until that next one, you know it, it's math and beats. I'm out.